Good morning. John in the background.
Hey, good morning, Doug.
How you doing, Raymond? Did you get my response to your question?
Yeah, I figured it out.
Awesome. A little zig when you should have zagged. All right. This is good news because today is your last installment of tests for convergence. What a strange world. And we will take a test. We're viewing tomorrow, take a test on Monday, and then we're going to go see what this can actually do now that we have played around with all of these extremely contrived little statements to see whether, if we add up infinitely many of them, if they actually add up to something. We're going to look at some that add up to something cool. So you're going to want to spend a good amount of time with that review and just kind of make sure you have everything kind of put together in your mind. I'm going to make the test. I don't know if the word is straightforward, but at least, I'm going to say use the alternating series test, or I won't just say, does this converge? I mean, I'm sort of skipping a section in the book where you sort of practice, which ones to use. So anyway, we'll review that tomorrow. No reason to belabor the point just yet. So let's share a screen and look at our last tests. You might be looking at your sheet and kind of staring here for a second at what the ratio and root test look like. And we'll play with an example to kick things off right now. See if the technology works for us today. What about that? What do you know? I'm in the mood to write on graph paper again. The engineer in me. So the final frontier, 10.7, the ratio and root tests. So let's play with an example to kind of kick things off. Let's say that you are trying to add up. That's a fine sigma notation right there. 4 to the k power over k factorial. This section includes some types of functions that we haven't played around with much before. And it turns out that this factorial thing is, part of you should think, why are you throwing factorials in there? We never studied those in any previous classes and so forth. But they show up incredibly prominently in what we're about to study. So you need to understand factorials. This is not just nerds at play, if you will. This is significant. And it doesn't really matter where we start here, but you can actually start at 0 on this one. Do you see why? You shouldn't. Usually we start at 1 if you just kind of generically say 1 to infinity, like every single time. You can start at 0 here. Did you find the factorial button in your calculator, by the way? This is very annoying. No, it's hard to find. I'll share a screen in a minute. I think I'll do it right now, as a matter of fact. I don't know as you'll need this a ton, and I really want to go kind of slow with factorial today and make sure that you kind of deeply understand what factorial is. It's very simple, but you can get a little overwhelmed by it in the concept of these problems. So let's see, second quit. So if I wanted to find, say 6 factorial, I think I said once before that if you go to the math button, and then it turns out it's over here under probability. That's kind of where it shows up. So it's very hard to find. And so there it is, factorial, 6 factorial, meaning 6 times 5 times 4 times 3 times 2 times 1, boom, that's 720. What about 0 factorial? Boom, 1. That's annoying. Boy, that is really annoying. Because 6 factorial makes sense. But certainly with 6 factorial, you don't go 6 times 5 times 4 times 3 times 2 times 1 times 0, because if you multiply by 0, then it'd be 0. So why would 0 factorial be 1? That's kind of annoying, but it is true. So for that reason, what I started with today, you can actually start with 0. That doesn't create 0 on the bottom of a fraction. Let me think off the top of my head. Do I have a good reason why 0 factorial is not 0? Well, I kind of do in the concept of probability.
Okay, there I am. Can't you work backwards from like 6 factorial is 7 factorial divided by 7, all the way down to 0 factorial?
That's right. In other words, you're dividing each time. That's exactly right. So there's sort of by pattern, a by pattern rule, or a by pattern sort of way of seeing that it has to be 1, even though it sort of feels like it wants to be 0. The other option is, let's say you're, I don't know, you're on Survivor, you're on Alone, that awesome series, and you're out there, starving to death. And so you're sitting in your hut thinking, what shall I have for dinner tonight? And you have nothing to eat. That's actually your choice. You still have one choice, nothing. So it's kind of a question of what do you call that? Do you say you have no choices, or that is a choice? Nothing is a choice. I think I'll eat nothing tonight. Yep. You have one choice there. So that's this kind of the probability reason. Anyway, that's not super important. But let's play around with that since we are over here in this lovely world. How do I get rid of this calculator? Same way as always. Let's take a look at this. So the problem was 4 to the k. So as per usual, I just want to make a few terms here. So it's 4, this cell will equal 4 raised to the k divided by, how do you get factorial in Excel? Unfortunately, I think I showed you this once before. You actually have to type the word fact. Notice it even says right there, returns the factorial of a number. So an exclamation point in Excel, that thinks that's English, like everybody else in the world. So factorial of that cell over there. And so boom. So let's see, does that make sense? Would 4 to the first would be 4 over 1 factorial? Yeah, that'd be 1. Except for in this case, we did start at 0, didn't we? So let's go back up here to stick a 0 in. We're usually starting at 1. So do you agree with that answer? Because that would be 4 to the 0 power. Hey, that's 1 over 0 factorial. Hey, that's 1 too. So it's 1 over 1. So I guess that is working. So let's see what's happening here. Let's watch them growing. So notice it went from 1 to 4. And remember, these are the AN terms. We haven't done any adding yet. These are just our kind of our terms. And so it went from 1 to 4 and then 4 to 8. Notice you might think, let's see what happened. It got 4 times bigger when it went from 1 to 4. It got 2 times bigger when it went from 4 to 8. And now 8 times what is 10? Well, that's even a smaller. Notice they're actually growing. It's still growing, but they're decreasing in size. So now, ooh, look at that. It didn't grow at all. What the heck? What's going on there? And then, wow, it's actually getting smaller now. Whoa, what's happening here? Would you agree in the beginning back here that it looked like there's no way that this series could add up to something because of, well, the divergence test. Like, what do these terms have to do in order to add them up and go to something? What do I need to see way down here? What kind of a number do I need to see down there if there's any shot
Smaller
of adding
numbers.
up? Yeah, really small. I need to see something like, something like that. I need to see tiny numbers, because otherwise there's no point in trying to add them. And so in the beginning here, it looks like, well, this is crazy. There's no way that this is going to add up to something. And then all of a sudden, it's like, hey, they're actually getting smaller now. This is very exciting. So if I drag this down a little further and drag these down a little further, hey, look at that. Started actually getting pretty small there at 15. So interesting, it actually grew for a while. Isn't that kind of cool? Grew for a while, stayed the same, then it started dropping off. And by the time I got down to 31, notice that number is really small. What's your intuition then, based on what you see there? Is this going to converge or diverge?
Should converge.
Yeah, doesn't it feel like it's converging, and really converging pretty quickly, because remember, that's 5.6 times 10 to the negative 16th power. That's point and then 15 zeros and then a 5. Like, this is really converging quickly now. And so just to equals sum, just to kind of cut to the chase, if I kind of grab all of these and say, what is that sum right there? Would you agree that's a pretty good estimate right there? And again, the good estimate is because, well, what's the next term in the sequence? The next term in the sequence is got 16 zeros in it, so it isn't going to get much bigger. Does that make sense? Now, again, as I've been pointing out the whole term, is kind of like, well, yeah, it definitely adds up to something. But the troubling reality of all this is, what does it add up to? Is there some, actual, not just approximation like I just got there, 54.598, but, is it 54.6? That would feel really satisfying. Or is it like pi cubed divided by 19 or some ridiculous statement like that? We're extremely annoyed by the fact that this doesn't seem to add up to something that we can actually find. And as I've said, often that's actually the case. And interestingly, in the next chapter, we're gonna actually be glad about that, if you will, or we're gonna be kind of, I don't know, maybe understand why leaving infinity in these problems is kind of neat. So the point is it actually feels like this thing should converge to something. And so kind of the ultimate question here is kind of why, or how do you show that, or how are you gonna, I don't know, kind of prove that? And again, I think it's kind of cool in the world that you and I live in with Excel that I don't know, what I just showed you is not a proof, as I've sort of jokingly said, thanks to GTF when I was in college. It's more of a poof. Like, it looks like it's going to converge to something. I'd now be ready to kind of make a bet on it, but true mathematicians are not content with kind of what we just did. And of course, most mathematicians never even had access to what we just did, playfully. And so it's sort of based on Excel. Ding, ding, ding. Excel would kind of imply convergence. Now, looking back at this statement right here, which of course is again a really weird looking kind of a statement. What's the mathematical name for that type of expression right there? What do mathematicians call that? If you have like, and again, maybe writing it like this looks a little bit better. You're used to it seeing it that way. What kind of an equation is that?
Exponential.
Exponential. And then this one down here is sort of brand new. It's factorial. We talked a little earlier in this class about growth rates. Let me go get a little just remind you of what we talked about before, because it's just going to show up here enough that we need to look at it. I just made a quick copy of the Excel page that we made. But when we were playing around with this a while back, remember this was the growth rates, and you can sort of see it happening. Notice, let's just to remind us a little bit, notice back here, maybe back at 3, can I write on this? Yeah, I can write on this. Notice it's kind of unclear who's winning. And, you know, off the top, you might say, and notice I chose 3. This is like x cubed. I'm choosing b to be 3. There's b. So this is like a cubed equation. Notice in the beginning, that polynomial equation is kind of winning the race. And it continues to be winning when you jump down to 4. And notice, however, though, when you get here, it's still winning, but look who's catching up. And notice it's whipping the exponential because the base of that is only 2. Right now, I chose the base to be pretty small. But notice by the time you get down to here, the exponential is now defeating the polynomial, even though the polynomial was cubed and the exponential's base was only a 2, yet it still starts to win. And so by the time you get down to the 12th step, you know, you're seeing the order that I put these in. Logarithmic is the slowest growth, linear is next, polynomial is next. Remember, linear is really, you know, x to the first power. Polynomial is just opening it up for that exponent to be anything else, 2, 3, 4, 5, 6, 7, 8, 9, 10. Exponential, where the x is in the exponent. But factorial wins. Factorial grows faster than exponential. Notice it's really easy to see right here. And in our case, didn't we have an exponential divided by a factorial? And so this is not, if you will, taught in your text, but I'm a believer, I think you've seen this, of kind of, you know, the concept of intuition. So, you know, armed with that knowledge, yeah, the bottom is going to outrace the top here. And so those terms are on their way to 0. And so based on that alone, I would say this is going to, you know, I could see that this might converge, if you will, even without looking at Excel. And again, I think it was fun to look in Excel and see the terms growing and think, what, you know, there's no way. But then all of a sudden, they drop off and tank. So that's kind of cool. Well, here's what the ratio test says. Actually, let's just look at it since we got it here. Maybe you already looked at it earlier. Bam, the last test. Let's see, what is this saying? The sum of AN. So what are we looking at this time? Well, notice the name of it, ratio. We're taking kind of the previous term, the ANth term, and then because of the +1, does it make sense that'd be the very next term after that? And we're going to divide them. Now, generally speaking, isn't it true, as we looked at, let's see, yesterday, I don't remember where we were yesterday. As we looked at yesterday, isn't the next term need to be getting smaller? Like each term's got to get smaller, right? So each term has got to get smaller, at least after some point. As I just showed you a second ago, was each term getting smaller in the beginning? No. But once we got that early business out of the way, then the terms started getting smaller, smaller, smaller. So I think that example in Excel was really important for us to look at. So if that's the case, if somebody said, hey, let's divide those things. So AN plus 1 is smaller than AN. What happens if you take a smaller number divided by a bigger number? What kind of a number do you get? 8 divided by 9, 10 divided by 15. What do you get if you divide a smaller number by a bigger number?
Not 1.
Yeah.
Less than 1.
Something less than 1. That's exactly what this test says. Like, notice how this is not that complicated. If you try to show this to somebody in your life, they're going to try to get away from you and think, what are you talking about? But this isn't that difficult. I mean, if you're looking at, that's why I love playing with Excel. If the terms are getting smaller, 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 then if I was to divide the next term by the previous term, I'd get something less than 1. That would be a way of saying they're getting smaller, 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 right? So that's what we do. For this particular test, if you have two functions that are really weird looking, and notice over here, let's see, it actually doesn't say this. I'll add this myself. Yeah, it does. This test is useful. It's useful when there are factorials or powers involved. It's a good test for that because they don't play well together. Like they don't act the same. And so by dividing them, we're going to be able to kind of actually prove, not just look at Excel, not just kind of use our intuition, but actually kind of prove that this is going to converge. So does the logic, and again, you have this sheet in front of you for the test. You need to memorize any of this stuff. And of course, it would diverge if that was bigger than 1, because of course, then you're getting, the terms are growing, right? If the next term is bigger than the previous term, then when I divide, I get something more than 1. Notice this is kind of, so it's kind of infinite or interesting. Notice it actually says that it's inconclusive if it's exactly equal to 1. In other words, it's kind of hard to tell because that'd be like on the line between converging or not converging. So it's like, I guess that test didn't help. We'll have to try something else. Okay. Well, let's try that test out with our problem. So we need to take, let's just go slow here to make sure that you see this. AN is our expression 4 to the K over K factorial. That would mean that A to the N plus 1 is, and I suppose I should be saying A to the K here since everything is K's and not N's, but so A to the K plus 1 would be, well, just replace K with K plus 1. And then we're going to divide these. And you don't have to memorize this, as I said, because you have your sheet, but we're going to divide the next term by the previous term, not the other way around. Okay, well, that's pretty easy. So 4 to the K plus 1 divided by K plus 1 factorial. And I'll be dividing by this fraction here. So isn't that the same as multiplying by the reciprocal? And you may note that the sheet did not just leave it there. It said, importantly, it said, what is the limit of this as K goes to infinity? In other words, what is this behaving like? And what we're looking for is an answer less than 1. If it actually approaches some constant like 2/3 or 8/9 or anything less than 1, then we could say this thing converges. So how's your algebra skills? First, what happens to, how do I get, I don't know, these two talking to each other? Do you remember your exponent rules? If you have 4 to the K plus 1, remember if you had like X to the second times X to the 5th, don't you get to add those? So if that's 4 to the K plus 1, then wouldn't that have been 4 to the K times 4 to the 1 then, since you add the exponents? Notice we're not used to going backwards. Here we're going backwards. We're actually fine kind of going this way. And so that's cool, because now I can say, hey, cool, these would cancel and that'd leave the 4 behind. In other words, 4 to the K plus 1 over 4 to the K, that's just 4. So I'm able to do something with this because we made a ratio out of it. What about this other business? What about k plus 1 factorial? Well, remember, factorial just means if I have 5 factorial, this seems, stupid to write this down. But what are we doing? We're just taking 1 away from it each time, right? And we stop at 1. So what's k plus 1 factorial then? Is it any different? No, it's k plus 1 times, well, 1 less than that, k. And then it would be k minus 1 and k minus 2. And the problem is this k is not a number, right? Like 5. So it's like, how do I know where to stop? I mean, is it like ... k minus 9,000? I'm just like never ending. Does that make sense? But think about, what you just wrote here. Really, that's k plus 1 times, well, isn't all of this here collectively still just k factorial? That's kind of the trick to this. In other words, on top, we have k factorial, and I don't have to do anything with it. On the bottom, we have k plus 1 times k factorial. Give you a second to make sure you soak that in. We'll do some more examples. That's really cool then, because bam, bam, those cancel out. I'll erase this, but just so that you kind of understand where this is going, if we had 6 factorial, of course, that'd be 6 times 5 times 4 times 3 times 2 times 1. And if we divided 5 factorial by 6 factorial, doesn't all of the 5 factorial part cancel, just leaving the 6? It's 1 more. Isn't that exactly what happened up here? Just looks weird, right? Like, slow down. This isn't hard. Don't look up formulas. Don't page through the book like trying to make sense of this, looking at some theorem or something like that. Like, just write it out. Like, this is not hard. It doesn't have to be hard. Okay, well, this is pretty exciting then, because what did this just become? Well, we just got that whole thing. What didn't cancel out? Well, we have a 4 on top and we have a k plus 1 on the bottom. So this is what this became. I think in your assignment, just to make sure that the wording is clear, I think your assignment calls this, I should probably look because I'm afraid I'm going to say this wrong. It seemed like it was kind of like, what's this function? They're like thinking of that as like a function. Like I'm dividing it and I get this new function. Well, notice it is a function because there's still like a k in it. Does that make sense? It didn't just come out 7. So they're saying, what does that function reduce to? Well, notice we got it to go to 4 over k plus 1. So what happens to that as k goes off to infinity? What happens to it? It goes to 0. In other words, it did approach a limit. What did our sheet say? It said if it approaches a limit that's less than 1, hey, ours approached 0. That's less than 1. So it actually approached something, and that something was less than 1, then you got it. Converges. Absolutely. So that's the proof, if you will. We saw it, we sort of knew it was going to converge based on what we saw in Excel. This is the proof that it actually is going to converge. 0. So L is 0. L is less than 1. So this thing converges. We don't know what it converges to. We know it's about 54. you won't see estimation in this section, which is kind of good because it feels like it'd be really painful. If you think about our ability to estimate, this probably isn't stuck in your head very well, but we said we could estimate it if you could take an integral. Well, wouldn't that be fun to try to take the integral of 4x over x factorial? Like how in the world would you take an integral of that? That was a technique for estimation. We can't really take an integral of that mess. And then the alternating series, this isn't an alternating series, but if it was an alternating series, we said the error is just less than the very next term. That's all we had to do is figure out what the next term is, and that's our error. So we can get an answer to this, but we sort of have no formulas to figure out, how good is our 54 that we got a few seconds ago. So it converges, but we have no idea to what. We can approximate it, but we have no idea how good our approximation is. But again, although we don't have kind of formulas for that, the cool thing is as we saw in Excel, hey, if your next term has got 17 zeros in front of it, then you're there. Like that's a good estimate, right? Like, awesome.
Does that change if we try to approach negative infinity?
Let's see. Yeah, is there let's see, was there any absolute value business on this? Ah, look at that. Boom, 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 boom. In other words, don't think about whether it's positive or negative. Treat them positive, individually positive, not positive after the fact, but individually positive. So your question is good. Now, does it make sense that, again, this is just intuition, but does it make sense because that's a 4 on top, which isn't changing, and the bottom has a k on top of it? Does it make sense this, well, fraction, if you will, this ratio, if you will, is going to go off to, it's going to go off to 0, if you will, pretty quickly, in the sense that the top's not, it's not like the top is growing and the bottom is growing. The top isn't growing at all and the bottom is growing. So this is on its way to 0, if you will, in a hurry. And that's kind of why we saw what we saw in Excel. Like it was ripping in that direction. So if we'd got not 0, but like 0.9, well, we still would have said it converged, but notice it's not a lot less than 1. Therefore, it's going to converge, but if you will, a lot more slowly. We got 0. That is way less than 1 if you in the ratio world, right? So our terms actually didn't kind of settle like they might have in a geometric series, like it's say 3/4. And we said, oh yeah, if they settle at 3/4, then that'll converge because their ratio is less than 1. Well, this ratio is 0, like the top number is 1 and the bottom number is 50,000. Yeah, that's going to converge for sure. That's the ratio test. Let's try another ratio test problem. Let's look at another example. What about this here? Fellow 5. Let's use n this time. N to the 6th divided by 3 to the n. And let's let n go from 1 to infinity. What if we didn't start at 1, but we started at 10? Do we care? The answer is no. Who cares? And again, what I just showed you in Excel is the important reason. What we care about is what happens way out there. Did you notice that those first terms a minute ago were huge, like 10s and 15s and big numbers like that? Well, that caused our sum to be like 54. But the important thing is just what happens way out there. That's what determines convergence. We in a sense, we say we don't care what it converges to. We just want to know it converges to something. So if I start at 10, fine, the first few terms are missing, but that doesn't change anything, right? It's infinity that's causing us the problem. I could start at 1,000 and it wouldn't make any difference. It doesn't matter what that number is. Could I start at 0 on this one if I wanted to, based on the equation?
Yeah. right? Because 3 to the 0 is still 1.
Yeah, that's right. 3 to the 0 is still 1. The top would be 0 to the 6th. The first term would be 0 over 1. It'd be 0. So yeah, 0 is a number. So I could start there, but I don't care. I'm not even looking at that. If it's a 6, I'm not even paying attention to it. Doesn't matter. Of course, if it's a book assignment, no one's going to give you something that makes no sense. I mean, you got to start where you can start. Anywho, what's your intuition? What type of function are these? Notice we don't have a factorial this time. And that note sheet said these are good for factorials and for exponents. So what kind of a function is that on the top? Again, you're not used to seeing it that way, but if I wrote it as 5x to the 6th, maybe that would look more natural. You're used to seeing x there, right? What kind of a function is that?
Exponential?
No, because the exponential's got to have the exponent in. The exponent's got to be the x. Does that make sense? 5.
It's called a
So-
power equation or a polynomial.
This would be exponential, but yeah, that's exactly right. This is just a polynomial equation. Like a squared equation is a polynomial, cubed equation. The exponent is a number. That's what makes it a polynomial equation. The bottom is the exponential because the letter is in the exponent. Well, based on what I just reminded you of, which one grows faster on the kind of list, the growth rate, kind of the rough growth rate idea?
Exponential?
Yeah, exponential outgrows polynomial. And notice it takes longer. Notice it's not outgrowing it by a lot here. It's only 4 times as big, but if I kept going a little further, it's going to start outgrowing it really fast. I don't know if that makes sense. So exponential is going to outgrow. So my intuition, which again, the book says nothing about. Exponential outgrows polynomial. So I'm guessing convergence. I'm guessing this converges just because of that. But again, the question is how to prove it. How do you actually show that that's the case? Well, this is the ratio test. So again, let's slow down and look at it. So our a to the n equation is as given. Our a to the n, our next is just to, well, add 1 to our number. So replace n with n plus 1. Replace n with n plus 1. And now I divide those. And so we are interested in this function of n. I think this is the way your assignment says it. And we're interested in the limit of it. This function of n where we have a to the n plus 1, which is this. And I'll go ahead and write this one all the way out, divided by a to the n. That's kind of our function, which is horrifying. Of course, we need to, reduce that and kind of figure out what does that thing look like. Well, of course, that would be dividing fractions. I skipped this step last time, but just to make sure you're feeling it, wouldn't this be the same as this? Let me give you a second to play with that yourself. Like, can you clean that up at all? Can you simplify that a little bit? Can you, get rid of some stuff to kind of show, yeah, remember, we're ultimately interested in what is the limit? What's the limit of this statement as n goes to infinity? And based on our guess here, we're expecting this to approach something less than 1. That would kind of prove it. But man, that's an awful mess right now. It's this whole thing we're taking the limit of. So I need to be able to simplify that some to, like we did last time, to kind of see what's that thing going to behave like. not easy. Do you at least agree with this? N plus 1 to the 6th times 3 to the n. That's really on the top. And then 3 to the n plus 1, that's 3 to the n times 3 to the 1 from the previous problem. So we can do that at least. And then there's still a times 5 times n to the 6th. And so at least I can say, hey, well, there's a few things that go away there, right? Bam, bam, 5, 5, those are gone. And now I'm, if you will, kind of stuck. But since both, so there's a 1/3, since both n plus 1 is to the 6th and n is to the 6th, can't you rewrite that as n plus 1 over n, kind of all to the 6th? There's again another algebra concept that you should understand, but watching me do it might be like, oh yeah. I saw Alyssa go, yeah, I see, that's true. And let's see, well, so the 1/3 is there, but again, isn't that a fraction? N plus 1 over n, isn't that the same as n over n plus 1 over n? Like if I just unadd the fractions, if you will. And so this is 1/3 times 1 plus 1 over n to the 6th power. Remember, what we really want to know is what is the limit as n goes to infinity of our statement. Well, now that we've simplified it down a little bit, we can actually address that, I think. Notice there's only one n left. So what is this statement? What is that statement on its way to if we let n be big?
0.
0. Therefore, this is really like 1/3 times 1 to the 6th power. Well, 1 times itself a bunch of times is just 1. So this is actually 1/3. Hey, look, it approached the limit. So this thing is on its way to 1/3. That's kind of cool. And that's less than 1. Not 0 this time, but it's less than 1. So L is 1/3. Cool, less than 1. So we kind of proved, if you will, that this will indeed converge. I want to just give you a chance to soak on this quickly by going back over to Excel and let's actually do this in Excel. Let's just see if we can get it to look like it. The ratios really are kind of going to 1/3. Does it look like that? Let's go blue collar here a little bit. Stuff isn't that hard. Share. So let's see, we got a bunch of terms over here. And our terms were 5k to the 6th, so equals 5 times k, which is this number here, raised to the 6th power. And then that was divided by 3 to the k, 3 raised to the k. I don't see anything wrong with that. So there's our first term. And notice it passes. And notice how interesting those numbers are. It's part of the reason I showed this to you. It passes the divergence test because notice the terms go to 0, but notice something really fascinating happens in the beginning. In the beginning, notice raising something to the 6th power is a big deal, right? That polynomial, I raised it to the 6th on my sheet a minute ago, it was to the 3rd. If you raise it to the 6th in the beginning, that polynomial is dominating the exponential, right? And notice these numbers grow huge, like it got up to 320 was its maximum. Like notice again, it looks like, wow, this thing is not passing the divergence test. The terms are not going to zero. As a matter of fact, there's rocketing up 1 to 35 to 135 to 250 to 321. But then notice it starts to slow down, and then all of a sudden, oh, look what's happening. Now the exponential starting to win and the terms start dropping off. And so again, it's kind of cool just to note equals sum. No one will ever know what this is. In a sense, I might be the first human that ever made up this problem before. So, no one's ever considered it, but notice the sum of this appears to be in the vicinity of 1863.75. And based on the fact that this is 5 zeros and a 1.0001, like the terms are getting pretty small down there. So that's a decent estimate, right? So it really is going to converge despite what happened initially. Now, what we're interested in though is in this ratio test, can we actually see this happening? So let's see over here. I'm going to say, let's do I want to know if you can think about what am I going to type here? The ratio test was the next term divided by the previous term, right? So all I have to do here then is say this cell right here is going to equal the next term divided by the previous term. Isn't that all I have to say? And notice early on, hey, that's way more than 1, not good. Again, all that means is terms are growing, that's bad, right? We need this number to be small, it's not small. But what happens if good news, right? Look, it's getting smaller. What this is telling us is growth rate. And initially it was growing, well, 21 times bigger, but hey, look, it only dropped to 3 times bigger. And now it's only 1.8 times bigger. And now it's only 1.2, but it's still growing. 1.27 is 27% growth. Don't forget, still growing. That's not good. We can't have this thing more than 1 because that would mean growth. That would mean it isn't working. That means it's not passing the divergence test. But then something wonderful happens right there. Less than 1. So the terms are now getting smaller. The question is, what is this approach? Notice it hasn't made it yet to 1/3. We said it would actually approach 1/3, right? And it isn't there yet. So, well, let's just drag this down a while. Now remember, infinity is a big place, right? So, but notice even at 345, I'm seeing it approaching 1/3. So do you see how our math worked? I mean, our non-blue collar method of doing the algebra, we saw that it was on its way to 1/3 without kind of having to manually do it. So that's kind of cool, right? Notice by the time you get down here, it can't even display it apparently. I don't know why that is. It's probably because I screwed up somehow. I don't know why that is. Oh, I see why it is. Look at the size of the terms right here. 2.2 times 10 to the negative 291. Like that term is so close to 0 that it's insane. So basically it doesn't even know, it can't even display it. The number is so small. So now it's trying to divide 2 numbers that are so tiny. It's like, oh, it just can't handle it. That's what's going on. So the other thing that might be kind of fun, just since we're sitting here, is just to visualize this. I've always kind of shown you this concept of, the graph, but it's just kind of neat to see visually what the numbers were just showing. And remember, this is a to the n. This is our individual terms. And so they grew, but then they dropped off. And so, okay, look, it's passing the divergence test. It's on its way to 0. That's kind of cool to see. And then let's quickly do the same thing with sum equals sum of these two cells. This is what I've done lots of times for you before. And we're gonna make that stay put so that after one step, our sum was 37, and then it grew to 172, and then it grew to 425, and it's on its way to 1863, right? We saw that earlier. So look, by the time it gets down here, it's like already accurate to 3 decimal places. Well, notice, of course it is, because look how small the numbers are. It's going to stay here. Don't you find yourself wondering if that's actually the exact answer to this now? Like, I mean, that's a nice answer, right? 3/4. I'm finding myself now wondering, is the answer actually exactly 1863 3/4? Is there some way to, that's a nice answer. It's not, you know, one of those ridiculous decimals. Again, though, the thing I think would just be kind of fun to look at is, you know, what is that? If I insert a graph of that again, notice it approaches it monotonically, like it's working its way up to it. It didn't go above it and then go below and above and below because there wasn't positive and negative numbers. It just kept adding something and it worked its way up to that. And so it's kind of leveling out up there. Isn't it kind of lovely, if you will? So play with Excel. That's why I keep showing you that, because your intuition about this is actually more important than these kind of technical details. Mathematicians would disagree with that statement, but I think you could leave this class knowing nothing if you didn't grow your intuition a little bit. Let's look at one more example that's, well, a little harder in terms of the algebra. You have a question like this in your assignment that I found, let's just say, terrifying. I didn't share. I must share. One last ugly looking example. Let's look at this. Let's take our time and do a perfect sigma. There we go. That's perfect. All right, let's do 5 raised to the 2n plus 4. That's again, that's an exponential equation. So it's a little uglier than just 5 to the n. Still an exponential. The letters in the exponent. Exponential on top. What's on the bottom? Factorial, except an ugly factorial. Do you agree this is going to converge? Just because it's exponential over factorial, just like the first example. Weirder looking, but this is going to converge to something based on our intuition. And so where do I start? Where do I start this mess? Well, we really don't care. 7, who cares? But can we use the ratio test? I'm going to give you a couple of minutes to try that. Can you write out what that would look like? What's the function look like that we're creating by dividing the next term by the previous term that we're then going to analyze to see if it actually approaches something less than 1? Two n plus 4 and the 3n plus 2 are hurting your brain right now. Hopefully you didn't write what I just wrote. If you did, think about what's wrong with what I just wrote. Not hard, just replacing n with n plus 1 to start with.
You added incorrectly, but you also didn't distribute.
Yeah, it's important that you realize you're replacing n with n plus 1. And so 2 is being multiplied by n. Well, now n is n plus 1. You need that parenthesis there. And 3 down below is being multiplied by n plus 1. Again, that's just kind of a dumb algebra mistake, but so hopefully you had something more like that. I hope you survived until what I have written now. Just double check yourself. But the question is, did you survive the slightly more complicated factorial nonsense and the slightly more complicated exponential nonsense? Were you able to break them apart in such a way that stuff could cancel out? This is not hard if you know your algebra. Many questions in your assignment are going to ask you to not just say converges or diverges. You may have noticed you have like 3 tries. And so if the problem just said, does it converge or diverge? Then you say converge. And if it's wrong, then you switch to diverge and now you got it right and you're done. I mean, obviously on the test, I'm gonna look for this algebra. So don't circumvent your learning here on your online homework. This is the logic I'm gonna want to see to show that you understand this. So they will ask you, as I think they should, they will ask you, you know, what is this thing right here? What does that reduce to? What does that clean up to? List that, and then go on and say it converges. Or actually they'll say, what does that simplify to? What's the function that simplifies to? Then they'll say, what happens to it as n goes to infinity? Oh, it approaches 5/4 or approaches 3/9 or whatever. And then does it converge or diverge? There's like three things you have to answer. So here's the important part that perhaps you blew. Do you agree that 5 to the 2n plus 6 used to be 5 to the 2n times 5 to the 6 because you had exponents, right? And therefore, the 5 to the 2n plus 4 would be 5 to the 2n times 5 to the 4th. Aha. So now there's some stuff that can cancel. But again, what about this 3n plus 2 and 3n plus 5? Your gut reaction to that should be like, oh, I'm kind of confused, but like, this is not hard. Just write it out. What do you do to find a factorial? You take the first term. There it is. There's the first term, 6 factorial. The first term is 6. And then what do you multiply that by? You multiply that by the next term. How do you get the next term? Take one away from it. And then take one away from it. And then take one away from it. And so on and so forth, right? Like that's all it means, except we just don't get to quit. So if that's true, do you agree that what is left here, notice the dot, dot, dot forever is included. Isn't that just 3n plus 2 factorial? So then if that's the case, we really have 3n plus 2 factorial on the top. And we have 3n plus 5, 3n plus 4, 3n plus 3, 3n plus 2, and so on and so forth. And so now I'm in a position to cancel some stuff out. I can say, boom, boom, those are gone. They're identical, that's one. And all of this and all of that are gone. What happens to 5 to the 6th over 5 to the 4th?
It just turns into 25.
That's right, 5 squared or 25. So I have 25 on top, which is not good, right? 25 is a big number. We were hoping for something kind of small, but notice what's left on the bottom is like a whole bunch of n's. And so although 25 is a big number, hey, there's n's on the bottom and n's are going to infinity. And so this thing is on its way to 0. Yes, 0. We found a limit less than 1. And so this is going to converge as we knew it was going to, because this is exponential and this is factorial. We knew the bottom was going to outgrow the top. We knew this was going to happen. We knew from the start, just based on intuition, this is going to converge. But now we just proved it thanks to the ratio test.
Real quick, for that top part when you were canceling the factorials, so you didn't take it out to 3n plus 1 for the upper part. Is that just because I guess the upper limit of your top factorial is what determines where you stop canceling on the bottom?
That's exactly right, because 3n plus 2 factorial means 3n plus 2 times 3n plus 1 times 3n times 3n minus 1 times 3n minus 2. And because it's not a number, that'll just go dot, dot, dot forever. So yeah, I stopped when I got the bottom to look just like the top. Does that make sense?
Yeah, I see. I just wanted to make sure we didn't forget to write 3n plus 1 or something.
Nope. So the very next term right here would have been 3n plus 1, and then there would have been a 3n. That's what the dot, dot, dot right there represents. So my point is that can look confusing, but just write it out. Just remember, if you know what 6 factorial means, 6 times 5 times 4 times 3, it's no different just because it's weird looking. The next term is just one less than the previous term. Write a few of them out. I mean, write the whole thing out. Write 3n plus 2 times 3n plus 1 times 3n times 3n minus 1. Write a bunch of those out. And then write a bunch of the green ones out. 3n plus 5 times 3n plus 4. And at some point you'll go, oh, look, it's canceling out from here. So all that's left. So again, not only does this converge, it actually converges pretty darn fast, because notice there's a lot of n's down there. Notice that's actually 3n cubed, actually 27n cubed down there if we were to multiply it out, because the constants don't make a whole lot of difference. So it's like 25 over 27n cubed. That's on its way to 0 in a hurry. It's not just on its way to 0, it's on its way to 0 in a hurry. armed with those 3 examples, I think you will hammer this assignment and have no trouble. Let's take a quick look now with our last few minutes at another test that's really kind of simple and quick. Fortunately, called the root test. What does it say? What does the root test say? This says, if you have some function, again, some equation that tells you how to develop your terms, and you take the nth root of it, and that approaches, again, a limit. L is standing for a limit, like some number. So in other words, you have some expression, you take the nth root of it, and right now that should feel like, what are you talking about? Why would I do that? Then exactly like before, it will converge. Notice this is identical. It converges if L is less than 1. It's exactly the same statement, no different. Everything about this statement and this statement, utterly identical. Why would you ever use this? Well, it's useful if you have something that has an nth power to it. We need to look at an example because that's not helpful. We saw it, but it's not helpful. All right, what would be an example of that? Well, something like this. What if you had the sum of a series, we'll say from n equals 1 to infinity, and it was 5n over 4n plus 18. Now, if I stop right there, prepping for the test in a couple of days, which test says that's not going to converge? Of all the like 7 or 8 tests we have now, which test does that fail?
You could use the comparison test to just make it equal to 5/4 a constant. Maybe that would work. I don't know.
You're right, which makes it there's an even easier test as a result. Again, what do these terms become? If I went to Excel and I said n equals 1, n equals 2, n equals 3, n equals 4, if n gets really big, what happens to that statement?
It stays in the same ballpark. The power of the bottom is 1 or smaller, so the overall power of the bottom is 1 or smaller.
But notice there's a power on the top too.
So does this fail the ratio test then?
To Ben's point, would you all agree that this thing pretty much behaves like this? In other words, we really don't care there's an 18 down there. We don't care if it was 18 million. We don't care if it's plus minus. Pretty much that thing behaves like that, right? Because the 18 is going to have not much value as soon as we get way out there. So if that's true and these cancel, that's what it's on its way to. In other words, these terms are on their way to 1.25. Does that make sense? So if we looked way down Excel, we're not going to see 0 down there. We're going to see 1.25, 1.25, 1.25. Well, if every time when you get down there, if you just keep adding 1.25 and adding 1.25 and adding 1.25, there's no way this can add up to something, right? This fails the simplest test of all, the divergence test. The terms don't go to 0 here. Does that make sense? So it's kind of comparison. In other words, you got to compare the fact that the 18 doesn't really exist. And so we need to remind ourselves of that. But, in this section, it's going to be, what if this whole thing was not just that, but raised to the nth power? Now, all of a sudden, it's like, oh my gosh. Now, even based on common sense, a second ago, we just said what's happening on the inside is going to 1.25, 5/4. But then notice this even makes it worse. In other words, now you have 1.25 inside. This is on its way to 1.25. But in order to get to that place, doesn't n have to be really large? Like, 2,000 or something? Like, what's your calculator going to say if you take 5/4 raised to the 2,000th power? You're going to get a gigantic number for this. So this even made it worse. Like, this is failing the divergence test, if you will. And that's kind of what this section is getting at, is if this number inside here is larger, that's wrong. If that number inside there is larger than 1, then this thing is going to be huge, right? But what if what was inside there was less than 1? What's your calculator say? Do that. What's your calculator say if you take 3/4 and raise it to some large power? 3/4 times 3/4 times 3/4 times 3/4. What's it say? Point
0.
2,000. Yeah, it says 0. It isn't 0, but it's like so close it can't even tell you. You see how it's actually, what we need is for the inside of that to be less than 1, because this n up here is going to get huge. And so do you see why? Do you see the intuition of this? Like what we need is, we could just like, who cares? There's an n up there. Who cares that that number is going to be 2,000, 2,800,000? What we really need to do is just check and see what's inside that. How's it behaving? Well, that's exactly what the root test says. It just says, hey, go take the nth root of it. Get rid of that. In other words, ignore it. That's really what the root test says, conceptually. So root is, of course, short for square root, cube root. So it's basically saying, if you're sitting here staring at that and you're going, I don't know what to do, then take the nth root of it. So if I take the nth root of something that is raised to the nth power, doesn't that just get rid of it? So that now this just becomes 5n over 4n plus 18. Again, that's technically what you're doing. All I was saying in English is just erase it, like ignore it. But that's just the technical approach. So if I take the nth root of whatever this an statement is here, this of course collectively is our formula, then just analyze this thing. Analyze this as n goes to infinity. If it's greater than 1, then it's going to diverge because that represents growth. If it went to 1.2, that's 20% growth, which means you're going to have more and more and more and more and more money or cats or whatever. If it's less than 1, then that means you're actually growing. Remember, 0.95 means 5% decay. You're actually losing 5%. So if this thing is less than 1, then it's actually going to converge to something. Who cares that it's raised to the 2 millionth power or whatever? That's what causes it to go to either infinity or to 0. Does this statement then at least make a little bit more sense now if you stare at what they're saying there? They're just saying, get rid of it. Get rid of that exponent. If it's raised to the nth power, get rid of it. And if you do that, and what's left behind as you let n get huge, if that settles on something less than 1, then the fact that you're raising it to the nth power will cause it to go to 0. Notice realistically, L is on its way to 0. It's like it doesn't have to be just less than 1. It's kind of on its way to 0, it would seem. Let's look at one more example, and then I think we'll be out of time. A sort of a slightly more complicated example, but only complicated algebraically, not complicated in concept. But what if I gave you this one, except for we made it a little more interesting, and we have n over 3n minus 7, except for what if this isn't raised just to the nth power, but what if it's raised to the 2nth power? Will that destroy your soul? How am I going to take the nth root of it? Do I take the 2nth root of it? Like, how do I? Does it make sense that conceptually, what you're really doing is just ignoring this? Like, okay, so it's 2n, who cares? That's going to be a big number out there, irrespective if I multiply it by 2, it just gets bigger faster. So it's like, I'm really, in a sense, I'm just staring at this saying, just kind of saying, what's going on here? Why can't I write? I'm just kind of saying, what does that behave like? As though that wasn't there. But watch this a little more slowly. It's just kind of interesting what happens as a result of this. So here's kind of the tricky part. Like, you can't take the 2nth root of it. Do you recognize that n over 3n minus 7 to the 2n power? What's the property of exponents? If you have x to the third to the fourth, what do you do in that situation?
Then you multiply the exponents.
Yeah, you get to multiply them. I hope you could explain why to somebody, not just some random memorization. If that's true, then isn't that a multiplication that has been done? So couldn't I think of this as squared to the nth power? Now it just has an n. Okay, great. So now I'll take the nth root of that expression, which I will. No, don't do that. Copy it. So now I'm going to come back and take the nth root of that thing, which of course is just going to cancel those. And so then I'm left with this statement to analyze: n over 3n minus 7. But notice it's actually raised to the second power. And I want to know what is that as n goes to infinity. Well, notice it's n squared over I guess that's kind of a dumb way to analyze it. Notice as n goes to infinity implies by the comparison test conceptually the same thing as n over 3n. Does that make sense? Because the 7 doesn't really exist and the n's cancel. So you end up with 1/3 to the second power, which is actually 1/9. This is on its way to 1/9. Notice it's not always 0. In this case, it's on its way to 1/9. And if you now put the n back in it, if you analyze 1/9 to the 2n power, and remember n is like 1,000, a million, a billion, whatever. Well, the very fact that that 1/9 is less than 1 means when I raise it to a high power like that, it's just going to go away really fast, right? It's going to go to 0 as a result of the fact that that 1/9 is less than 1. It's going to go to 0 for sure. Does that concept make sense? So again, your assignment will ask you for that 1/9. It won't just say, does it converge or diverge? And then you just answer and you're done. Like you gotta say, what is it? What's it approaching? 1/9. And then now, because that's 1/9, then you can say converges because it's less than 1. So that is our L. L is less than 1/9. L is less than 1. What am I talking about? L is less than 1. So we could say for sure that this thing converges. That's kind of fun. Converges. So you got to supply the logic, certainly for the test. All right, we're at 9:21. Let's get you out of here on time for a change. So if you want to get the most out of tomorrow, all I'm going to do is pull up the review and give you opportunity to ask questions, just kind of discuss things. Of course, the interesting thing here is can I put all this together? Like if I'm you, I'm thinking I can survive tonight's assignment with what you just showed me fresh in my mind, but on a test there's going to be like everything. And so it's a chance to kind of, can I stare at that convergence sheet of tests and kind of recreate my knowledge from previous sections, and then what are the problems going to look like? So that's me telling you what the problems are going to look like, the review that I've posted in my open math. So for those of you that are, I'll just show you this going out the door, but for those of you that are new to my style, where is it? You can't see it up there. There it is. Remove this thing. There we go. So I've got test reviews sitting in here. So all I'm going to do tomorrow is I have my own test review that I made, and I made it in concert with the test I made. So they're talking to each other. If you do well in this review, you'll do well on the test. If you don't do well in this review, you won't do well on the test. And all of my solutions are posted here. So if you're smart, you'll sort of spend some time between now and tomorrow identifying some of your problems. But you have all my answers, and it's all kind of my handwritten work, which is kind of showing you, what is it I think you should know? What is it I think you should understand? What do you need to be able to show to prove that something is converging or whatever? It's not just kind of a, take a guess. So those are in there waiting for you. So that's all we're going to do tomorrow. I'm just going to open that thing up. We're just going to play around with it a little bit, talk about it, reason about it. And hopefully that'll be enough and you'll kill it. And then notice I have right now, you can see this chapter 11, 12, 13, 14 are hidden from you because I'm still playing around with the questions I want to assign. So that's one of my jobs today, is to go make sure I like all the questions in chapter 11 that will start kind of next week. All right, stay after or out.
Thanks, Doug.
Thank you
Bye,
all.
Doug. Thanks.
Thank you.
Thank you.